This presentation is a life cycle analysis comparing dimethyl ether via different production routes by Cameron, Taylor, Madeline, and Samantha.
This project analyzes production routes for dimethyl ether, or DME, to determine its viability as an alternative fuel to low sulfur diesel and compression engines. Low sulfur diesel has become standard for the majority of vehicles requiring diesel fuel. However, there are many benefits that come with using DME instead. Some of these include dimethyl ether's lack of carbon-carbon bonds, a lower pressurized fuel injection, and its high volatility and cetane number. Because of the lack of carbon-carbon bonds as well as a large oxygen content, DME can more easily combust while producing less soot and black smoke compared to low sulfur diesel. The lower fuel injection for DME runs at 6,500 psi compared to 30,000 psi, making the required equipment less complicated and therefore much cheaper and safer. The high cetane number indicates a lower auto-ignition temperature and instantaneous vaporization, making it a better alternative for combustion to low sulfur diesel. One of the major drawbacks to DME is that the energy density is only half that of diesel, so twice as much is needed. DME also requires the addition of a lubricant which can corrode certain types of materials like elastomers, which are included in many diesel engines. In this project, there are two fully developed production pathways for dimethyl ether: dehydrogenation of methanol and direct synthesis from syngas.
The base case design involves the dehydrogenation of methanol, which can be performed using a high-temperature liquid catalyst or a low-temperature solid acid catalyst. The high-temperature catalyst can be a liquid acid polymer resin, which requires reactive distillation following the reactive step. A solid acid gamma alumina oxide can be used as a low-temperature catalyst for this process as well. This is primarily favored over the high-temperature catalyst because it favors the formation of DME at equilibrium conditions. Production of DME using methanol requires much less separation technology. However, it requires an expensive feedstock, methanol, which must be synthesized from another feedstock, such as natural gas.
The direct synthesis method using syngas is a much more viable production method because of the low cost of syngas as a feedstock. This method requires two catalysts working side by side: a methanol synthesis catalyst, copper zinc oxide alumina, as well as a methanol dehydration catalyst, gamma alumina. Using a bifunctional catalyst allows for methanol and DME synthesis to occur simultaneously in a fixed bed reactor. The benefits of a single fixed bed reactor include the low methanol concentration in the reacted medium, which shifts the reaction equilibrium to favor DME. This means that the reaction is able to run at a higher temperature and lower pressure than in other types of reactors. This does have a drawback, however, because it requires 3 distillation columns to be used, which in turn increases the overall capital and operating costs of the process.
As previously mentioned, the two feedstocks necessary for the production of DME are methanol or syngas. Methanol is very expensive, and the use of methanol as a feedstock requires purchasing or connecting the process to a pre-existing methanol synthesis plant. This process is much less complex and requires fewer unit operations. On the other hand, syngas, which consists mainly of hydrogen, carbon monoxide, and carbon dioxide, can be generated from a variety of sources such as waste emissions, steam reforming of coke, natural gas, and gasification of coal. The major drawback in producing DME from syngas is that it requires purging some of the recycle stream fed back into the reactor in order to prevent the buildup of CO2 in the process.
In addition to requiring less unit operations, the chemistry of the production of DME from methanol is less complex. The methanol to DME reaction occurs in a single step, while the synthesis of DME from syngas requires a series of 3 reactions in the same reactor. Traditionally, DME is produced from syngas using 2 reactors, but under the right operating conditions and the use of a bifunctional catalyst, it can be carried out in 1 reactor. The first reaction step involves the formation of methanol from syngas using a copper oxide, zinc oxide, and alumina catalyst. This acts as an intermediate step for the production of DME from methanol reacting over a gamma alumina catalyst, resulting in DME and water as products. The release of hydrogen, carbon monoxide, and carbon dioxide must be taken into consideration when using syngas as a feedstock. Despite these concerns, direct synthesis of DME from syngas has a competitive advantage because it is a greener alternative to low sulfur diesel.
There are 4 steps to a life cycle assessment. The first of those 4 steps is to determine the scope and boundaries of the study. The scope of this process defines its goal, and the goal of the study is to compare the production of DME from both methanol and syngas feedstocks. The functional unit for this study is 1 kilogram of DME. This functional unit is easily comparable between the 2 processes. It is often important to include the lifetime of the process as well. In this case, the lifetime is 20 years. Because of the different feedstocks used in the base case and the optimized design, a cradle-to-gate analysis study must be conducted. First, a gate-to-gate study was conducted and then extended to a cradle-to-gate study. The cradle-to-gate study not only looks into the impacts of the feedstocks, but also the energy sources and utilities for the plant and their associated impacts.
This is the process flow diagram of the base case retrieved from the design textbook. In this base case, methanol is reacted to form DME in a less complex version than the syngas feedstock process to DME. This process utilizes one reactor and two distillation columns. The distillation separates DME out in the first column and the methanol out in the second column. The methanol is then recycled to the reactor so that no feed is lost, especially since methanol is so expensive.
This table is the material balance for the base case. This includes all the stream components along with the temperature and pressure of all the streams. This is helpful in that all the materials can be kept track of during the analysis.
The reactor here is a fixed bed reactor that operates between 250 to 370 degrees Celsius. A mild exothermic reaction takes methanol and generates DME and water. Two columns are used to separate these components. The water out the bottom of the second column is a wastewater that is below the contamination level for methanol and is sent to finish being treated off-site. There is a total of 8 heat exchangers and 3 pumps in the system that will have emissions included in the energy balance assessment. Two tables at the bottom are heuristics used to calculate those emissions for the reactor, valves, pumps, and etc.
This table shows fugitive equipment emissions in the waste and purge streams for the base case. These were calculated using the tables from the previous slide. This helps visualize the breakdown of all the equipment and where the most emissions are coming from. Later, this table will be analyzed along with the rest of the impact factors in order to generate recommendations for the plant and how it could be optimized. This will conclude the inventory of inputs and outputs of the base case design for the gate-to-gate portion of the life cycle analysis.
This diagram summarizes the inputs and outputs of the production of methanol from natural gas. This will be used to determine the impact of the feedstock in the cradle-to-gate analysis.
This is the second part of the life cycle analysis of methanol from natural gas production. In this step, the inputs and outputs of the entire process are displayed in the diagram. This diagram includes materials, energy, waste, etc.
Here's the table of all input and output materials for methanol production. This was used to find the impact factors from the GABI-6 software. From this database, it is possible to find the total impact factors of the entire process.
Once all the total impact factors were found, they were graphed and compared to other processes such as methanol production from coal. The breakdown of where the majority of the emissions come from can be seen in the first figure, and a comparison of the process to other processes can be found in the second figure. From this comparison, we can see that the natural gas route releases the fewest emissions of the three processes compared. When expanding to a cradle-to-gate analysis, the energy and utilities used in the design must be accounted for. This table shows the different utilities of the process and what each equipment utilized in order to run. The feedstock of the system must also be accounted for and how the feed was made. Along with the production of the feedstock, methanol transportation must also be accounted for, which is about 250 miles. This analysis assumes that methanol is produced from natural gas. The tables on this slide are the total emission factors of the cradle-to-gate analysis. The first one gives all of the emission factors associated with energy, utilities, feedstock production, and transportation. The second table summarizes the actual emissions for the cradle part of the base case design.
This is the optimized case in which syngas is used to generate methanol and then DME. 3 reactions take place in the reactor, and the feed that comes out is made up of carbon dioxide, hydrogen, methanol, water, and DME. The product then flows to the first of 3 columns where CO2 and hydrogen are distilled out the top. The remaining compounds are then sent to the second column where DME is separated out. The third column separates methanol from wastewater, and then methanol is then recycled back to the reactor. This table is the entire material balance for the optimized system. It includes all the streams and their temperatures and pressures. This will be utilized in the gate-to-gate part of the analysis.
This optimized case utilized a fixed bed reactor at 330 degrees Celsius and completes 3 reactions at once using a mixture of 2 solid catalysts. The product for that reaction is then fed to 3 distillation columns to be separated. 7 heat exchangers are utilized in this process. The table at the bottom of the slide compiles the total emissions for the gate-to-gate analysis, including the streams that leave the control volume encompassing the plant.
The life cycle analysis was also found for the production of syngas from natural gas. This was used only in the cradle part of the analysis of the optimized design. This is a block flow diagram of the entire process. This process only makes hydrogen, but there is a significant amount of carbon dioxide also generated, which when combined makes syngas. Along with the block flow diagram is a plant data table. This table shows the total utilities to fund the plant, and from this, the impact of energy, steam, and natural gas can be determined.
The first table displays the average air emissions of the system along with the percent each part of the process emits. The second table displays the greenhouse gas emissions along with the global warming potential. These emission factors are used to generate the total impact factors. The material and energy effects of the process are displayed in these 2 tables. From these tables, the impact factors can be calculated once data from the Tracy database has been retrieved. This is an impact assessment of the syngas generation process. This table shows the different impacts and their stressors on the environment along with the major impact categories and areas.
Extending to a cradle-to-gate analysis, the utilities need to be accounted for along with their emissions. The table on this slide shows the rate of the utilities for each of the pieces of equipment. Along with the energy analysis, the production of the feed syngas from natural gas must be accounted for in its emissions. The transportation of syngas to the plant will also be accounted for in this analysis. The first table gives all the emission factors associated with energy, utilities, feedstock, production, and transportation. The second table summarizes the actual emissions for the cradle to part of the optimized design.
The third step of the life cycle analysis is to calculate the impacts of the materials used on the environment. The impacts utilized in this analysis include global warming potential, acid rain potential, particulate matter, eutrophication of air, ozone depletion potential, smog formation potential, ecotoxicity in air, and ecotoxicity in freshwater. The general equation to calculate the impact factors is displayed at the bottom. The assessment on this slide evaluates the impact factors from the entrance of the plant to the end of the process for both the base case and the optimized design. A summary of the cradle to the first gate impact factors for both the base case and optimized design are displayed on this slide. This impact assessment accounts for the raw materials being obtained up until the entrance of the process. The impact factors listed here are then added to the gate-to-gate analysis to determine the final impact factors for a cradle-to-gate analysis.
The results of the gate-to-gate life cycle analysis for the base case design are shown below. The results were normalized to obtain impact factors for a functional unit of 1 kilogram of DME. As seen, global warming potential and smog formation potential are the two biggest concerns. For the chemicals emitted, methanol, water, lubricant, and DME, there is no impact to acid rain, particulate matter, eutrophication, or ozone depletion. However, there were no ecotoxicity values given in the Tracy database for DME, methanol, or the lubricant, so it is uncertain if the impact of ecotoxicity is truly zero. From the spider plot, one can see that the largest impact to the base case gate-to-gate analysis is the smog formation potential. DME, methanol, and lubricant emissions all attribute to this impact. While DME has a larger impact potential, methanol contributes the most to the smog formation because of the large amount emitted.
The results of the gate-to-gate life cycle analysis for the optimized design are shown here. In this study, global warming potential had the largest impact. It is worth noting that this was 40 times larger than the base case design. The largest contributor to this high global warming potential was carbon dioxide. Carbon dioxide not only has a large global warming impact potential, but it was also the largest emission from this design, 21 times more than the next most emitted chemical. While there are impacts to particulate matter, smog formation, and both air and freshwater ecotoxicity, they are insignificant compared to the global warming potential. Therefore, action should be taken to reduce the factors contributing to global warming. In this design, the purge stream is the source of the most relief. Since all the components in the recycle react, it is suggested that the recycle not be purged at all. This would greatly reduce the effects of global warming from this plant.
Gate-to-gate analysis was extended to a cradle-to-gate analysis for both designs. The slide gives a summary of the cradle-to-gate analysis for the base case design. As seen, global warming potential rather than smog formation potential is the largest concern when the effects of the cradle are added. The largest contributors to the global warming potential were the emissions of carbon dioxide from the feedstock, methanol, production, and the production of steam from natural gas. The smog formation potential can be attributed to the emissions of nitrous oxides from both the feed and steam productions as well as transportation. Again, it is worth noting that there were no Tracy factors available for the ecotoxicity of air and water. Overall, the use of cleaner feedstock sources such as methanol produced from biomass could help to reduce the impacts of this design.
Finally, the results of the cradle-to-gate life cycle analysis for the optimized design are shown here. Similar to the base case design, global warming has the largest impact. Again, the global warming potential of the optimized design is larger than that of the base case. However, after factoring in the effects of feedstock production, energy, and transportation, the optimized design is only 5 times more impactful than the base case. This shows that the emissions associated with using a syngas feedstock are much less than that of a methanol feedstock. If the optimized design is improved by not purging the recycle stream, it is likely that the impact of the optimized design will be less than that of the base case.
The impact factors of the base case and the optimized design are compared in the tables of this slide. The base case design does indeed provide smaller impact factors per kilogram of DME production. However, the optimized case is more profitable design as determined in the cost analysis that was performed on both designs. If steps are taken to improve the optimized design and the emissions can be greatly reduced so that its impact is similar to that of the base case. The table to the right summarizes the energy contribution to the impact factors. Energy includes steam, electricity, cooling water, and refrigeration. From this, it can be seen that the energy contributions are significantly less for the optimized case. This is most likely due to the large emissions from the wastewater and purge streams. For the base case, nearly a quarter of the environmental impact can be attributed to energy use.
The main environmental concerns with each process were the global warming potential and the smog formation potential. In the gate-to-gate analysis, the optimized or syngas case had a larger global warming potential than the base case starting with methanol. In the cradle-to-gate analysis, the global warming potential and smog formation potential are both larger than the base case. These factors are the highest because of the amount of CO2 being released in the purge stream. After completing this life cycle analysis, the case chosen was still the optimized case because of its profitability. The methanol feedstock costs a lot of money itself and therefore cannot be considered a viable pathway for production of dimethyl ether unless that price decreases dramatically in the future. Though most of the factors indicate that the optimized syngas case affects the environment more negatively, the root cause of this is known. The purge stream is the major contributor to the amount of CO2 emissions in this process, and it could have been recycled. This would decrease both the global warming and smog potential factors and could make the process even more green. An analysis with this addition to the process should be performed before this process is incorporated into industry. Also, as always, being informed of new technology to reduce emissions can help benefit this process. These are the references used in this presentation.